Today we'll be talking about TLS. We said that TLS is a security protocol that provides authenticated confidential communication between a client and server. In this lecture, I'll go into more detail about the protocol itself. The Transport Layer Security, TLS protocol, is defined by an RFC, a request for comment. And the RFC describes TLS version 1.3 like this. TLS allows client-server applications to communicate over the internet in a way that is designed to prevent eavesdropping, tampering, and message forgery. A request for comment, which is abbreviated RFC, is a document that fully specifies a particular standard. For example, RFC 8445, which we will be discussing today, details and specifies the TLS standard. RFCs are numbered documents that are published by the Internet Engineering Task Force, abbreviated IETF. IETF is an organization that publishes and promotes the open, voluntary standards that govern how the Internet operates. The Internet is pretty amazing when you stop to think about it. It is this open network with a huge variety of systems that are able to communicate with each other. Any vendors or any individual can build their own server or their own client and will be able to communicate with the other servers and clients on the internet. The level of interoperability that makes the internet what it is pretty astounding, and we don't see this in other technologies very often. The IETF and the open standards it adopts is key to making this all work. Standards published by the Internet Engineering Task Force receive public review, and they also receive review and approval by a steering committee, the Internet Engineering Steering Group. And an RFC, a request for comments, can eventually be adopted as a standard by the IETF. Back to TLS. Remember that TLS runs at the application layer of the network protocol stack. We tend to think of it as being between the transport layer and application layer. And certainly, TLS runs over an established TCP connection. And remember that TCP is the transmission control protocol that operates at the transport layer and provides the logical end-to-end communication link between two communicating machines. So TLS runs over an established TCP connection. And once the TLS channel is established, the application data is transmitted over that channel as well. But in practice, it is the application layer that must be modified in order to establish the TLS connection. So we say that TLS is part of the application layer. The TLS handshake has three phases. The TLS protocol that establishes the TLS channel is done by a handshake, which has three phases. Key exchange is the first phase, and this phase establishes the shared keying material, the session keys that will be used to secure subsequent information. The parameters of the exchange are also established in this first phase. For example, in this phase, the client and server will agree on which version of TLS they'll be using. Everything after this phase is encrypted. In the second phase, server parameters are established. And the third phase is authentication. In this phase, the server is authenticated to the client, key confirmation takes place, and the integrity of the handshake is verified. After this phase, the application data, the HTTP requests and responses, can be sent over the TLS channel and will be secure. We're going to go through each phase. Phase 1 is key exchange. It starts with a client hello message, that's the name of the message, client hello, in which the client requests a TLS connection to be set up. The client hello is the first message of the TLS exchange. At this point, a TCP connection has been established between the client and the server, and typically for HTTPS, it is established at server port 443. But no HTTP requests or responses have been sent yet. Included in the client hello are a random nonce for freshness, the list of protocol versions that the client will support, a list of the symmetric encryption algorithms and key derivation functions the client will support, and it's listed here on the screen as the cipher suites, and a set of Diffie-Hellman key shares. Remember that in the Diffie-Hellman key exchange, each party contributes and shares with the other party over an open line their own exponent. Remember, Diffie-Hellman allows for two communicating parties to share numbers, exponents, over an open line, an unsecured line, and at the end of the Diffie-Hellman exchange, each party knows a shared secret key that no one else on the line can know. Even though, the communication is open and unsecured at this point, the endpoints, the two communicating parties, at the end have a shared secret key, but anyone listening to the communication does not know that shared secret key. That's what Diffie-Hellman provides. So the last part of the client hello is the client's Diffie-Hellman key share, the client's exponent. Later, the client and server can each combine the exchanged key shares to create their shared master key. There is an option in TLS 1.3 to resume previously established sessions, and in that case, there is a pre-shared key label, which is sent as part of the client hello, but that is not shown here. So the next message in the key exchange phase is the server hello message, and that's what this message is called. It's called server hello. The server replies with a random nonce for freshness, and the chosen parameters, so the protocol version and cipher suite selected from the set that was offered by the client. The server should always select the highest protocol version that the client offers. For example, if the client offers TLS versions 1.2 and 1.3, the client says, the browser says, I can support TLS version 1.2 and version 1.3. The server should select TLS version 1.3, the highest offered version. The server also sends their Diffie-Hellman key share, their exponent. And again, it's not shown here, but in the case where the client wants to resume a session and has sent a pre-shared key label, the server would then confirm the pre-shared key label that it will use. So at the end of the key exchange phase, the master key has been established and all subsequent communication between the client and server is encrypted. However, the handshake is not complete and server authentication has not been provided yet. That is, unless client and server are resuming a previously established session, which I'm not showing here. But in this case, where it's a new session that they are establishing, at this point, or at the end of this phase, communication is encrypted, but server authentication has not been established. Okay, the next phase is phase 2, and in this phase, the server must send the encrypted extensions message. This is the first message that is encrypted under the established session key, and it contains parameter information in response to what the client said. So these are parameters that are not required for establishing the session key. Remember that in this phase, data is already being encrypted, so we already have established the keys. But these are parameters that are required for the handshake overall. For example, information about the certificate types to be used might be included in this message. The server can also send a request for a client certificate, and this is optional. The server can request that the client send over their certificate, which would be used to authenticate the client's identity to the server. But for web traffic, for HTTP over TLS, this option is rarely used. The last phase of the TLS handshake is authentication. In this phase, the server authenticates itself to the client. The server sends over its certificate. The certificate verify message is a signature, the server's signature over the entire handshake, so over all data that has been sent up to this point, using the private key corresponding to the public key in the certificate message. So in this way, the client can check the authenticity of the signature and know that it is communicating with the subject named in the certificate. The server then sends the finished message, and this is a MAC, a message authentication code, over the entire handshake, so over all data sent up to this point. This message provides key confirmation, and it binds the server's identity to the exchanged keys. And then finally, in the TLS handshake, after the client verifies the certificate verify message, and the MAC, the client will send over their own finished message, which is a MAC, and it's a MAC over all the data in the handshake up to this point. So this last finished message from the client provides key confirmation to the server and binds the client's identity to the exchanged keys. Remember that the client is not authenticated to the server. The client did not send over its certificate, but the server still needs to know that it is communicating with the same endpoint that it started this TLS handshake with. The finished messages provide each side evidence of integrity of the entire TLS handshake and demonstrates knowledge of the shared key by the other. Now the TLS channel is set up, and application data, the HTTP requests and responses, can be sent securely over the TLS channel. TLS provides an encrypted, authenticated channel of communication between the client and server. The session keys established in the first phase are used to encrypt communication, and the server certificate authenticates the server to the client. It is important that the Diffie-Hellman session keys are fresh. They cannot be reused. And it's also important that old session keys are securely deleted once the session ends. So not just deleted, but removed from memory. So no remnants of the key remains in memory in either machine, so at either endpoint. This provides, if the Diffie-Hellman keys are ephemeral and removed at the end of a session, this provides perfect forward secrecy, which means that an encrypted session remains secure even if down the line some other session becomes compromised. An attacker who is somehow able to break the confidentiality of one session will not be able to learn anything that lets them go back and learn any information about messages exchanged in prior sessions. So this is the power of TLS, and this is HTTP over TLS, or HTTPS, which uses Diffie-Hellman and certificates and the PKI infrastructure that we've discussed, the certificate authorities that we've discussed.